Welcome, everybody. So here we are. I'm very pleased to be introducing Dan Spielman, who is virtually coming to us from Yale, where he's the Sterling Professor of Computer Science and Professor of Statistics and Data Science. He's won a lot of major awards, including the Doctoral Dissertation Award, 2 Gödel Prizes, a Fulkerson Prize, an Evelina, Polya, and Held Prize, as well as the Simons Investigator Award and MacArthur Fellowship. I first went to a talk by Dan when I was a graduate student, which must be over a decade ago. And I was blown away. I thought it was the best CS talk I've ever been to. And I still think that he's my favorite computer science speaker. I always come out of his talks thinking, like, Jelani, what are you working on? And why aren't you working on what Dan is working on? So I'm very excited to hear about what he's been working on now. And yeah, please take it away.
So today I'm going to be telling you about algorithmic discrepancy for randomized controlled trials, or using algorithmic discrepancy for randomized controlled trials. So this talk is based on a paper called Balancing Covariates in Randomized Experiments Using the Gram-Schmidt Walk. It is joint work with Chris Harshaw, who's a graduate student who'll be finishing in the fall and coming out to where you are in Berkeley to the Simons Institute. Frederick Savy, who's a professor in political science at Yale, and Peng Zhang, who's a postdoc who's finishing up, and I don't know if it's public yet what job she has accepted, so I will not say. During the talk, I'm going to skip most historical references because you can find them in the paper and it will describe them much better. There is one I really want to call out, which is this paper called the Gram-Schmidt Walk, A Cure for the Banachik Blues by Bansal, Dadouche, Garg, and Lovett. It introduced a really amazing algorithm called the Gram-Schmidt Walk. And you see, we put it in the title of our paper because it is what we are going to use. My goal today is to tell you about 2 things that look like they should go together and the work we need to do to actually make them go together. The first of them is discrepancy theory. This is a topic that's been studied a lot in combinatorics and computational geometry. It can be summarized as the study of how to divide things into groups that all look similar. I'll be more precise in a moment. But the main thing we can say in discrepancy theory is you can do much better than random. As a matter of fact, that's often how we quantify what the guarantees of discrepancy theory give, by comparing to what would happen if you divided things at random. But then we have randomized controlled trials. These are the way we usually evaluate the impact of all sorts of things. Everyone today is thinking about vaccines and medications, but we also use it to evaluate public policies and all sorts of interventions, which is how I got to thinking about it. And I'll tell you how I got to thinking about it a little bit more. So it looks like there should be a relation between these things. And there is, although it's not necessarily the first relation you think of, but what you really need in order to make it concrete and usable is the right algorithms. So I'll tell you some about how we can use the right algorithms for discrepancy theory to improve the design of randomized controlled trials. Okay, so let's start with a cartoon of discrepancy theory. For me, everything that I care about is going to be a point or a vector, one of these. And I say discrepancy theory tells us it's possible to divide them into groups that approximate the whole. Now, let's say I want to divide these points into 2 sets. I could do it. I could label one of them green and one of them orange here. And we have to choose what we mean by approximating the whole. Right now, let's just consider the average of the points. So here's the average of the green points. Here's the average of the orange points, or their center of gravity. Here's the average of the entire set of points. So I'd say this division, the green points and the orange points, approximate the whole because this point is pretty close to that one, and this point is pretty close to that one. If you want to be more algebraic about it, let's turn this division into groups into a vector. So let's say I have n things. They could be subjects, vectors. I will define a vector z. And just to fix notation, when I talk about a coordinate of a vector, I put that in parentheses afterwards. So z of I is the ith coordinate. Let's make it 1 if I is in group A, and -1 if I is in group B. We'll have 2 groups. And now if I want, I can write down the difference of the centers of these 2 groups. or difference of the average, it is, well, there's a normalization constant, but it is the sum of the z of i's times the vectors x of I, and that is this vector here. And if this vector is small, then we can think, well, then we know that the center of group A is close to the center of group B, and therefore they're both close to the center of the whole. So we can think of those groups as similar. Now, what I told you is that discrepancy theory gives you ways of doing this that are much better than random. So to make sense of that, I'll begin by taking a look at what happens at random. And first, let's begin by just examining basic facts about a uniform random vector z that's with plus minus one entry. So, right, I should have said independent entries, each chosen with probability half to be plus or minus one. If I take a vector z like that, we know that if I take a look at the sum of the entries in it and their absolute value, on average, that's around root n. If you want to make a more precise statement, we actually look at the square. If you look at the expectation of the square of the sum of the zi's, that's exactly n. Okay, but that's just a random vector z. Now let's consider dividing things up. So let's imagine, since I'm talking to EECS, we have people who are either computer scientists or electrical engineers in the audience. So let's make a vector, call it x, whose ith position is 1 if that person is a computer scientist, and -1 if they are an electrical engineer. And I can divide them into two groups. That division will be represented by z, and I can now look at the expectation of the sum of the xi's times the zi's. That'll tell us what is the average, the discrepancy between the average, say, number of computer scientists minus electrical engineers in both groups. If zi is independently chosen plus or minus 1, it doesn't really matter what xi is. Xi times zi, that product will be independent. So again, the square on average is n. Okay, that's just thinking about one quantity and one random vector z. As opposed to discrepancy for points in the plane, let me talk about discrepancy of vectors. And to make some computations easy, let them be plus minus 1 vectors. So imagine that I have n vectors, and each of them have entries in plus minus 1, and they live in d dimensions. If you want to think about what's going to come later when we talk about trials, imagine these are n experimental subjects about which you have measured d binary quantities. So let's see what happens if we take a random sum of these vectors, or sum with random signs. So we choose the vector z uniformly at random from plus minus 1 to the n and look at the sum. So just again, since xi is a vector, this is, say, the sum of z of 1 times vector x1 through the sum of z of n times vector xn, we get s. And let's look at a coordinate of it. By the previous computation, we know that the expected square of every coordinate is n. And the expected maximum entry, actually, it's pretty tightly concentrated. It's around root n times log d, where d is the dimension. So that's what happens at random. An amazing result published in a paper by Joel Spencer in 1985 called 6 Standard Deviations Sufficed proves that there exists a much better z. Joel Spencer proved that there always exists a vector z so that the maximum of the coordinates of s, that should have been with parentheses. You can see I've been talking to different audiences. The maximum coordinate of s is at most 6 times root d. So typically d is much less than n. He had different results for d larger than n. But if d is much less than n, then this root d is much, much smaller than you get by a random vector. And that's one way of understanding how we can say that there exists a vector z that is much better than a random vector. And this was one of the foundational results in discrepancy theory. Many people usually think about the case where d is equal to n, in which case this is still better. There's a log d term here where Spencer has a 6. Okay, so this, I say, was a foundational result, but what was frustrating was it was an existence proof. And for a long time, we did not have an efficient algorithm for finding such a vector z. As a matter of fact, people began to speculate that it could be computationally hard to find such a vector z. Until a breakthrough result of Nikhil Bansal from 2010. Bansal came up with a polynomial time algorithm for finding such a vector z. It wasn't with a constant 6, it's a bit larger. But it still told us that this is actually something we can do. And this sparked an enormous amount of work in a field we now call algorithmic discrepancy theory, where there are many, many other results in discrepancy theory that were previously just proofs that something exists. And following on Nikhil Bansal's work, people found ways to come up with efficient algorithms for finding them, which is really nice if you're a computer scientist, because if you want to use something, it helps to be able to find it. Just knowing existence is often not sufficient. Okay, so I should mention my connection with this work, and it'll be relevant in a minute, is I worked with Adam Marcus and your colleague Nikhil Srivastava to prove or resolve the Cadison-Singer conjecture. That statement can be understood as a problem in discrepancy theory. But instead of trying to divide up two groups of vectors so that their means are similar, we were looking at the moments. So you can imagine the sum of the squares of inner products in any direction. Let's not dwell on it, but let me just mention that there was, and there still is, no efficient algorithm for this. So what we have is an existence result. But while we were working on the project, we did develop a lot of heuristic code. And it works on many cases. And that proved very useful. Let me tell you how. So I told you about discrepancy theory. I'm going to tell you a little about randomized controlled trials. And the way I'll do it is I will tell you about the problem that got me into the field, because I didn't know there was a problem here until 4 years ago. So at Yale, I run the Yale Institute for Network Science. It's an interdisciplinary organization. My co-director is Nicholas Christakis, who's a professor in sociology and public health. And one day, Nicholas came to my office with a problem. So he was setting up a trial to test out maternal health interventions. So these were going to be done in rural villages. And the idea was how to get people in these rural villages to adopt different behaviors that would improve maternal health outcomes. They had 176 villages in Honduras, which is a lot of villages, but they were trying 16 different interventions, which meant that they had to divide these 176 villages into 16 different groups. And that would give you only 11 villages per groups. And so here's an example I give of a random division of these, divided by color code. I hope everyone can see colors. They discovered something that most of us know as the law of small numbers, which is that if you choose things at random, but you don't choose too many random numbers, you sort of see patterns in them. So for example, if you look at this random division at all of the red groups, they're all on the western end of the country. And that was a concern to Nicholas, because he said, well, what if that group is the best or the worst? How do I know if that's due to the treatment they're getting or something going on in the west of the country? Another group was basically in a middle latitude, same worry. So random was unsatisfying. And I said, well, okay, I can help with that. I mean, I should first tell you before how I got into helping with it. What are the standard ways of dealing with this? One standard way is, let's say we didn't have 16 treatments. What if you just had 2? If I just had 2 treatments, one thing you do is matching. Like you divide up the villages into pairs that are nearby if you can, maybe like this. I find a matching in this graph. And then what you do is for each pair, you flip a coin. And let's say for this group, I flip a coin. If it comes up heads, I assign that one +1 and that -1. For this pair, if it comes up tails, I might assign this -1 and that +1. You do that independently. And if there are good matches, that will actually be pretty good if you're dividing into 2 groups. But they had 16 groups. So what were they doing? They were trying to find blocks. They were trying to divide these villages into blocks of 16. That's approximately 16. And then shattering those by in each group, assigning, each group of 16, dividing them among the 16 treatments. And that was not looking good for them. So that's really what they came to me with. The problem is much worse than this. They knew a lot about these villages. They had been studying them for many months to get ready for the trial. They'd measured many things about them. I've learned that the things that they measure about their subjects are what statisticians call covariates. Since I didn't know that until 4 years ago, I'm defining it for you now. The things we measure are covariates. Things they'd measured that they thought could be relevant to maternal health outcomes or the functioning of the study included things like the distance to a hospital, the time it takes to reach a hospital, both on an ordinary day and when it's raining. And the rain can make a big difference in these rural villages. Things like median income, average age, percent female in a village, all sorts of socioeconomic factors, altitude, which varies a lot across Honduras, various measures of the social networks connecting people in villages, because fundamentally their study was social. They were trying to get people to change behavior. So they had a lot of covariates. When you measure enough things about your subjects, no two of them seem similar. I mean, it's not clear you would have been able to find reasonable matches between them to even do a matching once you measure all of these quantities. But hey, I had some heuristic code that was good at balancing things. So I said, okay, give me all your data, we'll balance everything. Actually, I first said, how many years do you have to study this? And he said, we have 3 weeks, people are on the ground. Okay, that's when I pulled out the heuristic code, said, okay, we'll try this. So I gave him this division that balanced the villages very nicely. This is just the geographic picture, but if you look at any of those other quantities, they're balanced very nicely between the different treatment groups. And then Nicholas asked me, could this be bad? It's like, could it be that the output of your algorithm is somehow going to skew the results of this trial in a way that is just not obvious from looking at this picture? And my first reaction was, who hurt you? Like, what algorithm did you use that caused you to be so suspicious that they could be doing something perversely bad? But I understand now that that perspective was wrong. He was right. So randomization is really important. The first reason is, at the end of the day, we want to make probabilistic statements. We want to say things like, the chance that the results of your study are due to chance is unlikely. Okay, that did not come out great. It never does. But we want to say that the results shouldn't be due to some poor assignment. And that's a probabilistic statement. In the end, they want to put confidence intervals on quantities or say something about p-values. To do that, you need something random. What this balancing gets you, well, okay, it gets you 2 things. One, it sort of makes it harder for referees to point at your paper and say, oh, that is skewed, I'll reject your results. But they shouldn't do that. What it really does is, if you balance this covariate information, it can get you smaller confidence intervals, that is, higher precision estimates of your treatment effects when the covariates predict outcomes. And my main goal here in this talk is to give you a way of balancing covariates so that when covariates do predict outcomes, we get smaller confidence intervals. But I also want to be good in the worst case. So we want to guarantee that we can never be much worse than your gold standard of a truly uniformly random division assignment. I should also say, what I got to understand was that this problem is really not an optimization problem. I was thinking this is a discrepancy theory problem. I want the division of optimal discrepancy. Maybe you can view it as a discrepancy problem, but really what you want is not the division of optimal balance. You want, in some sense, a distribution on assignments that's as good as can be. But
I wonder if I can interrupt at this point,
please,
because this is really interesting. And you said it had nothing to do with COVID, but I see the connection to COVID.
Oh.
Suppose they do a randomized trial and they say, well, we're just going to assign the different treatments, or the drug that does nothing. What's that called?
Hydroxychloroquine. Oh, yeah. So, okay, I'll address this for you.
Here's my point, is that it's obvious that if you do it at random, you might get randomly a lot of old people.
Yeah.
And you know that age has a huge amount to do with this.
Exactly. So when you are
Okay,
doing
so the
studies,
worst
right,
thing is to do it at random, but if you don't do it at random, you can kid yourself in other ways. So
right.
that's what you're really solving.
Yes. So okay, so I should say two things about that. One, the difference in medical studies is people are coming into the study one at a time. And usually when they come in, you need to assign treatment on that day. The techniques I'm going to tell you about work assuming you know all of the covariates in advance and you know all the subjects in advance. The online problem is what we've been working on for the last year. And I think we've solved it, but I'm not making any promises because we don't have all the proofs. But yeah,
Okay, I'm happy
if you're right. Like if there are things that you know that are relevant, like age, you want the distribution of ages to be balanced between your two groups.
exactly.
And you want to balance other medical conditions too.
Look, I'm okay if you solve the problem when you know everything in advance.
Okay.
Please tell me what the solution is.
We will get there. I should mention, since you were asking a little about the COVID trials, so I don't remember which was which. If I remember correctly, between Moderna and Pfizer, one of them just assigned people, well, I say basically flat out at random, subject having the same number in both groups. The other one divided people into three groups. So there was sort of a young, an old, and a people with comorbidities, and then balanced between all three groups. But it was still very, really just putting in three buckets. That was very crude. Okay, so what I did for Nicholas at the time was I gave him 100 balanced but very different assignments, measuring some notion of difference, and at least let him pick something random. And you can use that to construct confidence intervals. But I said that was 3-4 years ago. Now I finally know the right theory to explain and analyze what you should do and an algorithm that does it well, provably, reliably, in code you can download. So let's treat this mathematically, and we'll do it in the Nyman-Rubin potential outcomes model of experiments. I should tell you that if you talk to people who study experiments, there are many different models they study. I'm going to look at this one because it is the most conservative. It is the hardest one to deal with. And as an outsider, that seems like the way to go for me. So for simplicity, let's imagine we're dividing people into two treatment groups, a test group and a control group, or villages. And in this model, we assume that there are two potential outcomes for each subject. So if subject I is put in group capital A, we observe little ai. If subject I is put in group capital B, we observe little bi. We cannot observe both of them, and that's the whole problem. You cannot put someone in the test and the control group and see what happened to them. So you can only observe one. In the Nyman-Rubin potential outcomes model, we assume that this little ai and this little bi are fixed in advance, but unknown to us. So what that means is the only source of randomness that I can use to make any probabilistic statements is the assignment to treatment and control. So that is, we're not assuming the response to treatment is random. We're just going to rely on the assignment. Okay, now if you prefer to work in some model where little a of I and little b of I are random, you can do that. Just sample the randomness before our analysis, which you can, because what happens to a person is sort of like a box that you only know when you open it, and you can assume the randomness happened when the box was over here or over there. You don't care until you open it. So we're just going to assume that the only randomness we have on which to base any probabilistic statement is which group someone winds up in. Now, I've talked so far really about three designs. When I say design, I mean the distribution of the sets A and B. The first one is the one I'll call uniform. That's where you flip a coin for each subject and put them, say, in group A with probability half, and do that independently. If you're doing it with small groups, that could be disconcerting because there's some chance that group B is empty or group A is empty, but it's unlikely. Sometimes you want to balance. In that case, you let A, say, be a uniform random subset of half of the subjects. The other design I described was matching, where you form disjoint pairs among the subjects I and J, and then for each pair, you either assign I to A and J to B, or I to B and J to A, independently with probability of half. These designs, and the one I'll talk about later, all have the property that the probability that any subject is in group A is a half, They're just not necessarily independent. Only in this case is it independent. All the others, it will be carefully controlled. I should say, though, if you want other probabilities, at least with the design I'll tell you about, you can pick any probabilities you want and we can accommodate it. So the simplest thing to consider measuring in a study like this is the average treatment effect, or that's what we want to measure. We'll denote it by tau. It's the average of A of I minus B of I. So it's the average of the effect of putting subject I in group A as opposed to group B. Again, the problem is we can't actually compute it because we never learn both A of I and B of I. We just get A of I sometimes and B of I sometimes. We're going to consider estimating it by taking the sum of the A of I's for those that we observe for I in group A, minus the sum of B of I's for I in group B, and multiplying it by the right normalization factor, which is 2 over n. So this is called the Horvitz-Thompson estimator. Many of you know this as this, if you have to estimate a sum of things, but you only see them with some probability, you reweight them by the 1 over the probability you see it. And the great thing about the Horvitz-Thompson estimator is it is correct in expectation. Its average does equal what you want to measure, the average treatment effect. Oh, I forgot to say, the standard in this community is a hat appears on top of something if it's an estimator. So tau hat is our estimator of tau. I want to point out there's a very natural estimator we're not using, which would be the difference of means. The other thing that would be natural to use is take the average of the little AIs for those you observed and subtract off the average of the little BIs for those you observe. The main reason we're not using that is it's more complicated to analyze. And in particular, it's not even right in expectation. I suspect it should be possible to analyze the Gram-Schmidt walk design under this estimator, but I don't yet know how. So if someone figures it out, please let me know.
Now, isn't this the thing that you just showed us that you don't, isn't this what the government officials were doing to validate the COVID vaccines?
Oh,
well, they were taking
so
the best, the average of one, the average of the other, and they said the vaccine works.
It's a good question. So the thing is, these are the same if the two groups have the same size. I mean, sorry, these two estimators are the same and you can correctly adjust them if you know the sizes of the groups in advance. They're only different when the sizes of the groups can vary. Yes, in some of these trials, they did use this. But again, when you're dealing with 40,000 patients, the error that you get here from not having the right exact expectation is very small. And if you're using a very simple design, then it's not so bad to analyze this difference in means estimator. It's only when you go to something complicated, like I'll show you in a bit, that it gets tricky. But yes, difference in means is a natural one to use. Okay, but of course, we care about much more than being right on average. We care about the precision, which is what is the probability that tau hat differs from tau by too much? And actually, we care about more than that. If I tell you the precision is great, it's really small, it's very unlikely to deviate, the estimator's wrong, that still doesn't satisfy an experimentalist because what they have to do is they have to produce a confidence interval. So they also need an algorithm to estimate quantities like this when they're done. Because it's, I'm not telling them I can never say it's always great. You just say it's usually great, and then you got to look at the data and produce a confidence interval. So those are really the two sorts of things we're going to worry about. So let's see how we get at the error. Again, we should start with an arithmetic expression for the error of the estimator. So we want to care about tau hat minus tau. I'll multiply it by n for scale. We can write it as the vector z, which was the vector that was 1 or minus 1, depending on whether or not subjects were in group A or B, times the sum of the two potential outcome vectors, A and B. I'm going to use this vector, the sum of the potential outcomes, A and B, so often we're going to give it a name. So we'll call that mu. So that's really all we're going to use about the potential outcomes when we analyze error. This result is a little counterintuitive to some people, so I put a proof down here. I don't think it's worth going through it. Just know that there is a proof. And then you won't be bothered that sometimes many people's intuition is it should be A minus B, but it's A plus B. Okay, so that's our formula for the error. So we can see geometrically now a lot of what we want to understand. So the error is 1 in n times z transpose mu. You think about the inner product of z with mu. If I was using some deterministic algorithm, which I was, the sort of thing Nicholas was concerned about was that there is some chance that z has a big inner product with mu. What if z points in the same direction of mu? Then the inner product is big. And we know that doesn't happen if you pick z at random. I mean, if mu is a fixed vector and you pick a random z in high dimensions, it will be almost orthogonal to mu with very high probability. The angle is sort of pi over 2 minus 1 in root n, where n is the number of subjects. So this is why random is generally good. To make that more precise, well, there are a number of ways we can do it. The first one we learn is by using Chebyshev's inequality. We begin by taking the variance of the estimator tau hat. That's the expectation of the square of tau hat minus tau, the expectation of the square of the error. And then Chebyshev's inequality tells us the probability that tau hat minus tau is too big, more than any constant times the square root of the variance, is at most 1 in c squared. That's at least a bound you can use. There are better bounds, and we'll talk about them later. But to just sort of show improvement and ground computations, let's just think about variance for now. So let's take a look at the variance of the error. It is, well, the error is z transpose mu. So the variance will be 1 in n squared times the expectation of the square of z transpose mu. If we rewrite that as mu transpose z times z transpose mu, and then move the expectation inside, we get this quadratic form. It's got the vector mu on the outside, mu transpose on one side, mu on the other, and this matrix z on the inside, which is the expectation of the outer products of the vector z with themselves. So z, if it's a column vector, this is a row vector, this is a matrix, we'll call it capital Z. So here's the point. When we choose the design of our experiment, we are choosing capital Z. So we can know z, but we don't know mu. So our goal is to choose z that's small in some way. Okay, z is the covariance, sorry, capital Z is the covariance matrix of little z. That means that the ijth entry of the matrix capital Z is the expectation of little z of I times little z of j. When I say we want this matrix to be small, I'm thinking of using an inequality like this. The mu transpose z mu is at most the squared norm of mu times the 2 norm of the matrix Z. And if you're not used to these norms, well, I can say in this case, you're probably used to it. Z is a sum of symmetric outer products, so it's positive semi-definite. That tells us this 2 norm is actually the maximum eigenvalue of Z. So that's, we'd like to be small. Okay, we want to choose that to be small. Let's see what happens when we look at the independent design, because that's the benchmark we at least want to be sure we can beat. If Z has IID entries, then we can know exactly what Zij is in expectation here. When I is equal to j, z of I and z of j are both the same, either 1 or minus 1, you get a 1 in that case. Otherwise, because they're independent, we'll get a 0. So this matrix Z is exactly the identity. And if you plug that into the previous formula, that tells you that the variance of tau hat, the estimator under this IID design, is 1 in n squared times the squared norm of that vector mu, which was a sum of the potential outcomes. Now, I just want to tell you that if you don't make any assumptions, you can't do any better. By which I mean the following. If you give me any design and compute the matrix Z, its diagonal entries will all be 1. They'll all look like the identity. Which means that the matrix Z does have an eigenvalue bigger than 1. Which means if you give me any other design, there is going to be some potential outcome vector mu on which the variance of the estimator is higher. Okay, so to be clear, the IID design, we know exactly what it does, and we know that any other design can be worse. To get lower variance, you need some assumptions about mu. Now, I started out by saying people often don't use the IID design because one of the groups could be empty. Instead, they balance the groups. Let's see what that does here. what happens if we use a random balanced design? So that means I'm going to pick a vector z with plus or minus 1 entries, subject to the sum of the entries being 0. Here is the covariance matrix we get out. Let me not get into the matrix. Let's see what it says about the variance. There's a leading term in the variance of a 1 over n minus 1 squared. For the IID design, we had 1 and n squared, so we lost a little there. 1 and n minus 1 squared is bigger. On the other hand, the other term is smaller. So in the IID design, we had a squared norm of mu. Here we have mu minus the average entry of mu. So we've taken mu and recentered it so that the mean is 0. This is a projection, so it will have a smaller norm than mu. And sometimes it's much smaller. For example, if all your potential outcomes, A and B, you knew were going to be positive numbers, then mu will all be positive. And if you take a vector that's all positive and you subtract off the mean from all the entries, well, for most such vectors, that decreases the norm a bunch. So this is an advantage of the random, or tells you at least when you would want to use a random balanced design. Okay, the point of this talk, of course, is that balancing covariates can improve precision if they are correlated with the outcomes. So let's put in some covariates. I'll now imagine that for each subject, 1 through n, we have a d-dimensional vector. I will assemble them into a matrix I call capital X. So the columns of capital X are the covariate vectors for the subjects. And I claim this will be useful if mu is close to the row span of X. Let's start out by thinking about an ideal case. What if mu is actually in the row span of X? In that case, I can write mu as X transpose times some coefficients beta. They tell us the combination of the rows that achieves mu. If I then plug this expression into the expression for the variance of the estimator, I get another quadratic form, but now has beta on the outside and this matrix XZX transpose on the inside. And we have the problem that I don't know beta. So what I'm going to do is I'm going to try to make this matrix small. That is exactly what the Gram-Schmidt walk algorithm of Bonsall, Daudush, Garg, and Lovett does. So they gave a polynomial time algorithm that on input some vectors, let's assume to normalize, let's say their norms should all be at most 1. It chooses a random vector z so that the 2 norm, or largest eigenvalue of this matrix XCX transpose is at most 40. Now, for their purposes, they were just really happy to get a constant here. And I'm going to have to skip the slide in which I tell you about their purposes, but if people want to know more, it was for results in discrepancy theory, and we can do it in the question and answer session. They were just happy to get a constant. Now, for our purposes, we were not happy to get any old constant, because whatever number you get here is going to appear in the width of our confidence intervals. So a lot of our paper is dedicated to actually getting this down to 1, and that's optimal. You can't do better. So let's see what this tells us about the variance of the design. Still, let's look in the ideal case right now when mu is in the span of the rows of the covariates. In that case, we now get that n squared times the variance of the estimator is at most the squared norm of beta, whereas it would have been the squared norm of mu in the IID design. So is it smaller? Because I want to say we're much better than random. I should at least convince you that in a lot of cases, the squared norm of beta will be much smaller than the squared norm of mu. Like if the covariates were a random matrix, that would happen. Or you'd get the cleanest analysis if you assumed that each of the columns has norm 1 and say the rows of the matrix are orthogonal. If you assume that, then the squared norm of beta is smaller than the squared norm of mu by a factor of d over n. And that'll be small as long as the dimension is much less than your number of subjects, which we hope it is. Okay, but that was the ideal case. Let's see what happens in general. So in general, the way I'm going to look at this is I will see how close is the vector mu to the row span of the covariates. Let beta be the coefficients that minimize that. And Let epsilon be the part that's not explained by the covariates. You can now express your variance again, and expanding, writing mu is equal to epsilon plus x transpose beta, you get a quadratic form in Z, but with epsilon as the vector as opposed to mu. You get a quadratic form in XEX transpose with the coefficients in beta, and a cross term that you just sort of hope goes away and we're going to ignore for now. The first lesson here is you want the 2 norm of Z to be small, and you want the 2 norm of XEX transpose to be small. And if it is, then you can get this upper bound, then let's worry about the cross terms later. Now I'm going to tell you, you can't in general make the norms of both of these matrix 1. Making one small pushes up the other, but you can get a trade-off. And that's what we call the Gram-Schmidt walk design. So we choose a parameter, phi, in between 0 and 1, that balances how much we care about making Z small with how much we care about balancing covariates. And then what we do is we run the Gram-Schmidt walk algorithm on what we call these augmented covariate vectors. We have the xi's, but we put on top of them an elementary unit vector unique for each subject. And we scale them by root phi or root 1 minus phi to decide how important they are. I should also mention we randomly permute the order of the vectors. That is not for any purpose the Gram-Schmidt walk algorithm thinks about, but it facilitates computing confidence intervals later. So here are the guarantees we get. First, the 2 norm of the matrix Z is at most 1 in phi. The 2 norm of XEX transpose is at most 1 in 1 minus phi. So you see, we can make one small at the expense of letting the other be bigger. But we then get this amazing expression for the variance of tau hat. The variance of tau hat is at most 1 in n squared times the minimum over coefficients beta. Although this is a term I would have called epsilon before, but I don't know it in advance because it's a function of beta. It's 1 in phi times the squared part of squared norm of the vector mu that's not equal to beta x, plus 1 in 1 minus phi times the squared norm of beta. But again, I want to emphasize, we don't compute this, and we can't because we don't know mu. This is just an artifact of the design. So this term, many of you will recognize. This is really a ridge regression, or other people call it, solving a regularized least squares problem. You're trying to find a vector beta that represents mu in the span of x or get as close as possible, but you want to penalize the coefficients beta. If you think about phi, when phi is near 1, and I'm going to tell you now, that's the case of interest. When phi is near 1, this is big, small, sorry. When phi is near 1, this grows big. And this is going to be small when mu is near the span of x. So the closer mu is to the span of x, the bigger you're going to want to make phi. If you have any reasonable model, we can do all these analyses without models, but if you have any reasonable model and n is sort of big, then your best choice of phi is going to be close to 1. Essentially, the reason is that if you imagine n growing in some model, beta is not going to change because that's the coefficients, but this term is going to grow with n. You'll make phi near 1. So what happens is the right choice of phi gets you something that is very robust. When phi is near 1, you can never be much worse than the IID design in robustness, but you're going to be much better. You actually are going to get variance comparable to epsilon squared. That is the part of mu not in the span, as opposed to the norm of mu squared. So I guess the message is, you can get things that are robust estimators that can't be much worse than IID, but can be much better when mu is close to the row span of x. And of course, we don't just care about variance. And really the work of Ansaldo, Dushkarg, and Lovett actually was not to get at the variance. I lied a little bit. They instead proved that this vector x times z, the sum of the zi's times the x's, is root 40 sub Gaussian. So meaning you have tails that are smaller than a Gaussian. And most of our paper is actually dedicated to proving that it's actually 1 sub Gaussian. You can't do better than that. So I'm going to skip telling you about the algorithm or why we do it just in the interest of time. I'm sorry. I should first just tell you, like, why can't you improve on this, or can you? One, if you're thinking about variance, there's going to be a problem. If you care about the 2 norm of this matrix, well, consider the case in which X is just the identity with a bunch of zeros attached on the side. Then XEX transpose is going to be Z. And we know the diagonals of that are 1, so it's going to have an eigenvalue of at least 1. So you can't prove this is less than 1 in general. If you don't like that example, you can construct others. Like one consequence of this statement is that the squared norm of XZ is always at most D, the dimension. So if I make X a matrix which has the identity repeated a couple of times, you can also see that you'll never get this to be less than D if it's an odd number of times. You can also ask, can I do something better on any given instance? Like if I have a matrix X, can you give me an algorithm that will do better? In general, no. Charikar, Newman, and Nikolov proved that's an NP-hard problem. So they proved that it's NP-hard to distinguish 2 fundamental cases. One, when you have a matrix X for which there's a plus minus 1 vector Z, that when you multiply by it, you actually get the all 0 vector. We can't tell that from the case where the norm of the result is always at least some constant times D. And then I should mention what I just told you is about precision, but what you really need to do in the end is make some confidence intervals. And that we do by observing that this formula comes from a quadratic form in a matrix in mu, and we give a way of estimating that from the observed outcomes. That is the one part of the paper that I really wish we knew how to do better. But we might actually need a different design before we improve that. I don't know. So to conclude with a few comments. First, what should you do in practice? First thought is, you can include functions of the covariates. You don't have to include the raw covariates. You can transform them. You can take products of them. You can have them interact. You can weight the covariates. That's what I did to help with Nicholas's studies. Some we thought were less important. We gave them lower weights. You can construct hybrids of designs. For example, if there are really good matches among your subjects, you still want to make all these choices for each pair of them. You can use the Gram-Schmidt walk design to make those choices and get lower variance than you would if you made them independently. If you're ever going to pick a design, let me just point out, you can do a lot of simulation of different designs. Oh, I wrote X here. That should have been a Z. Pick any design you like. You can estimate this covariance matrix Z, and then take a look at what you think are reasonable vectors mu, and spend the time to see how each of them does. That's certainly what I would recommend doing if I were going to choose a design for a study. I mean, we spend so much time on these studies, we may as well spend some computer time on picking the best design. A very natural question is, should you use some sort of machine learning or even simple regression to adjust tau hat? And I always urge caution when doing that, because when you do it, you could also make your estimator much worse. And you do have to pre-register how you're going to compute your estimators in the end. It can cause trouble. At least I don't know a really safe way to do it, but I will say, at least for now, that's already going on under the covers if you use the Gram-Schmidt walk design. The variance of the estimator tau hat is already upper bounded by this result of a ridge regression. Okay, some ways to improve this. As I said, we've been working really hard on the online version of this, and I actually think we can handle the online version where patients come in as well, or just almost as well as the Gram-Schmidt walk handles the offline version. But yes, until proofs are finished, I make no promises. Really, people should consider other relations between X and mu. We're just considering linear relations here, but there are all sorts of other relations that I hope we can come up with designs that would exploit them. Again, I don't know how. Well, okay, Chris says there are a lot of cases where you're using kernels that are pretty straightforward. Smaller confidence intervals. Again, and this is both a question of how do we compute the confidence intervals? How do we prove they're correct? And maybe there are variations on the Gram-Schmidt walk design or entirely different ways of solving this problem that would get smaller confidence intervals out in the end. So it's not just knowing that we're precise under all sorts of circumstances, but being able to compute how precise we are when we're done. And also, there's even room to improve the trade-off we get, I think, in the room between the norm of Z and the norm of XEX transpose. I don't think our augmented vectors are the optimal thing. or maybe they are, but certainly we don't know how to prove that yet. They're within a constant of optimal. And usually us theoretical computer scientists proclaim victory when we're within a confidence of optimal and constant of optimal. But here this constant actually factors into the width of someone's confidence interval. So you should make it as small as you can. If you want to read more, we have a very long paper on arXiv. And actually, I should say there are two papers in arXiv, really. The first version we wrote with a very computer science style exposition, which I like, but Frederick didn't. So we rewrote it more for experimentalists and statisticians. And the second version, it's longer, it's like 130 pages, but it also includes more results in different simulations. But if you try to read it and it doesn't make sense to you, try V1 first. And we also have packages that implement this in Julia and R on GitHub you can download. And the algorithm is very fast. As I sort of implied, it's related to the Gram-Schmidt walk, and the time to compute the design is comparable to the classic algorithms for Gram-Schmidt orthogonalization. Thank you.
Thanks very much. Let's have some applause. Okay, so I'm really shocked at what I've just heard because we had the most important clinical trials that to influence all of humanity. We just had it, and there was no level of sophistication for how they ran the trials. They didn't take any of this stuff into account. In one case, you said they just chose the placebos at random, and in the other case, they did take some of the other confounding variables, but very minor ones, into account by dividing into three groups. I mean, this is pathetic when you realize that these clinical trials are influencing what everybody in the human race is going to be doing in 2021. So how can it be that that this was acceptable to people who are supposedly sophisticated, namely national governments?
So I'll give a few answers. One, if they were willing to wait 5 years, I'm sure I could have given them something better. But that was unacceptable. And really, we're using very recent developments from the last 3 years in algorithmic discrepancy theory. Okay, another answer is I want my biostatisticians to be conservative. Like, I would actually be somewhat upset if one of them just adopted our paper. It's still being refereed. And I did say it's 130 pages. Okay, many people have gone over the hard mathematical parts, I'm pretty sure, and people have sent us simpler proofs. I'm pretty sure it's all right. But, should the biostatisticians just trust their math friends? They really better verify our code is right. There's some questions there. I'm okay with conservatism on that. But also, I'm actually not sure if what we're doing or any variation of it would help, because when you think about the way the COVID trials are running, well, what they're doing is they take this huge group of people and they give them all the drug or placebo, but actually in some sense, then there's another random selection going on for who's really in the study. The people who are really in the study are the people who are exposed to COVID. And that was a really small fraction. If you think of these studies, less than 200 people out of 40,000 developed COVID symptoms. So in some sense, it would be doing a lot of work to divide these people into two groups and then having this random COVID coin picking actually who's been exposed. So given that the level of exposure was very low and a lot of randomness went into who was exposed, I'm not so concerned. And the results are very striking. Okay, we got lucky. These vaccines work incredibly well. As someone said, you don't have to be a data scientist to see that they're doing something good. There will be other trials of other things where it might be worth being sophisticated. If people are trying to do things like trials of, does one of these vaccines reduce the spread of COVID? Say within a context like a nursing home, you could imagine studies that I've seen proposed where they're going to say, this nursing home is going to get one vaccine, this nursing home is going to get another, and so on. If you're doing things like that, then you might want some techniques like this. But again, I'm not offended if people want to wait for it to be refereed.
Okay, so Anant has a question. Anant, I'd like to ask you to unmute and go ahead with your question.
Hey, yeah, great talk. I just asked it on the, since you're out of time, I'd love to see the slides on Gram-Schmidt walk. Yeah,
Okay. So the main thing to know about the Gram-Schmidt walk algorithm is it's trying to find a plus minus one vector. The way it does it, though, is continuous in the sense that it's just going to look inside the unit hypercube. And they begin with the zero vector. So they begin with the zero vector, and then they carefully choose a direction in which to walk. Maybe my picture here is missing something. What they do is they pick a direction like this, but they then walk one way or the other. So the direction is picked by algorithm, and then they either deterministically, but then it's a random step. Do I go this way or that way? And then they go until you hit the boundary of the hypercube. And once you hit a boundary, now one of your variables are 1 or -1. And then they say, okay, we're going to stay on that face. We pick another direction. We pick a direction in that face, and we go this way or that way. And say they go this way. And now suddenly two variables are 1 or -1. And they do that until they hit a corner. And now all the magic goes into how they pick that vector. What's sort of interesting is they knew that such distributions exist that met their guarantees before constructing the algorithm. So the reason they were constructing this algorithm is they were trying to de-randomize or come up with an algorithm for something called Banachik's theorem. Think of it as Spencer's theorem on steroids. It says if you have some convex set, you need it to be big. So we give a lower bound on its Gaussian measure of at least a half. And I give you a bunch of unit vectors. Then there is some signed sum of them. Well, you want to say the signed sum of them lives inside the convex set. You can't say that, but you can say it lives within 5 times the convex set. So this was a theorem of Banachik's that was known. There was no algorithm, but a few years before now it was Dadushkar, Glovett, and Nikolov had proved that Banachik's theorem is equivalent to the existence of distributions of vector z such that this sum was a sub-Gaussian random vector. And then what Bansal, Dadush, and Lovett did is they came up with an algorithm. They used that to then come up with an algorithm for constructing this sub-Gaussian distribution. And actually, if you want to see an exposition of how their algorithm works, I have done it in other talks you can find that were longer talks to audiences of computer scientists or mathematicians.
So Dan, out of curiosity, the getting down from 40 to the optimal constant 1, did that require changing the algorithm at all, or is it exactly the same?
It's amazing it doesn't require changing the algorithm, because I will admit when we saw the root 40, we said, okay, this algorithm's not going to do it. You know, like I can't tell an experimentalist, I'm sorry, your confidence interval won't be more than root 40 times the ID design, right? So we didn't consider their paper at first. We looked a lot for other algorithms. And then at some point we implemented their algorithm and noticed the constant was 1. So it doesn't require changing the algorithm at all. It's an amazing algorithm. It did require changing the proof a lot because it's a martingale concentration sort of thing. But again, we're getting the optimal result because we can't afford to use any of the standard inequalities because all the standard inequalities always lose something. So yeah, the technique we use, I can't summarize it in a nice soundbite yet, but might be useful for proving concentration in martingales because it's nice that it does give an exact sharp result.
I have to say I'm very surprised by this talk because I expected it to be mathematical and kind of hard to see the connection to humanity. But this has a very direct connection to humanity because it's how you design clinical trials or any other type of test of a hypothesis. So it's very important and certainly encourages me to dig a little deeper into the subject. So I'd like to thank you again for joining us. If you were with us in person, we would now be taking you to dinner and continuing the discussion. But hopefully, thanks to the trials, we're all going to get vaccinated, and starting in about a month, we'll be able to do everything in person. Things are changing very rapidly now. We appreciate it very much, and I love your style of presentation. It's terrific. Thank you.
Thank you very much.
Thank you, Dan.
See you next year in Berkeley.